Well, thanks for that introduction, Ben. Today we are going to be talking about non-Newtonian fluids. Um, you should all be seeing my presentation here as we build it. Gloop, glop, and oobleck, just kind of funny fluid names because sometimes non-Newtonian fluids are called funny fluids. So the goal of today's presentation is really to give everybody a kind of foundation in what non-Newtonian fluids are and how to model them using AFT software. Non-Newtonian fluids as kind of a general topic can be kind of overwhelming to people because they're so different than what most of us are used to. But once you get past that initial kind of learning phase and kind of really understanding what it means to be a non-Newtonian fluid, they're not too complicated to understand, though sometimes getting the right data for them may be a little tricky. And certainly once you get them into AFT software, um, it's a breeze to model them and to really look at what they're doing. So today's presentation, we're going to talk about three major topics. First, we're going to look at just kind of a general introduction to non-Newtonian fluids, what they are, what it means to be non-Newtonian, what it means to be a viscous fluid. Then our second topic, we're going to look at non-Newtonian fluids in AFT software. We're going to look at a few different viscosity models that we offer. We're going to look at some example systems, both in Fathom and in Impulse. And then we're going to, or I guess at the same time as we look at those example systems, we're going to look at some unique behaviors of non-Newtonian fluids. This part of the presentation is kind of my favorite part because it's really cool what those non-Newtonian fluids do and how they behave in your system. And then we're going to close off this presentation talking about rheological data. We're going to look at some test devices you can use to get that data, or that that may have been used to get the data you have for your system. We're going to look at the data that AFT software requires, and then we're going to look at some potential data forms that you might have, and kind of chat a little bit about what it might look like to put those data or put that data into AFT software. So we'll go ahead and get started with our first section, just an overview of non-Newtonian fluids. So the most fundamental question we have to ask is, what is viscosity? And viscosity can be described as the characterization of momentum transfer within a fluid. Put differently, it's the resistance to deformation at a given rate. So one way to think about fluid flow inside a pipe is, let me go ahead and put my laser pointer on. But one way to think about fluid flow in a pipe is that the fluid flowing in your pipe in the cylinder here is really just a series of fluid layers moving past each other. So in this diagram here, we've got our z-axis, the kind of axial direction along our pipe, and we've got this R direction as we go from the middle of our pipe to the outside. And as the fluid moves along through our pipe, we have these series of fluid layers moving at different velocities past each other. And since, for example, this inside cylinder or layer is moving faster than this next one, as those two layers are sliding past each other, they have some resistance between them. They have some friction or some, kind of inertia behind them that wants to, have that resistance. And so our momentum transfer, we can describe as, or we can write for the equation as tau RZ, our shear stress tau, acting in the radial direction, being applied in the z direction, is equal to negative mu, our viscosity, multiplied by duz dr, where uz is our velocity in the z direction. So what this equation says is that as our fluid layers move past each other at a different velocity, there is some amount of momentum from this layer being transferred to this next layer out. And that transfer is tau RZ, and it's described by the gradient of our velocity, the change in velocity in our R direction, multiplied by some constant, mu. In this case, it's our viscosity. And so basically, we're just saying that this viscosity is the resistance to this deformation, this gradient or shear rate. And now momentum transfer, on its own might be something that most people are pretty unfamiliar with, at least the math behind it. Fortunately, we can make a good analog to K, our thermal conductivity. So heat transfer, we can say that the heat rate in our x direction is equal to our negative thermal conductivity, or our resistance to heat transfer, multiplied by our thermal gradient, dt dx. So just like the total rate of heat traveling in a given direction is equal to the forcing function, our heat gradient, or our temperature gradient, multiplied by the material's conductivity, we can say that our momentum transfer is equal to the velocity gradient multiplied by the material's ability to conduct or to transfer that momentum. So that's a pretty fundamental description of what viscosity is, and will kind of help us set up what the rest of our discussion on non-Newtonian fluids. So with that understanding of what viscosity is, we can ask the second question: what is a non-Newtonian fluid? Well, these diagrams down here below are images or figures that some of you may be familiar with. On the left here, we have our shear stress tau plotted against our gamma dot, our shear rate, which is the same as that duz dr term we saw earlier. And here we can see how what it looks like to have this momentum transfer in our different fluids. So when we say that we have a Newtonian fluid, we can say that tau, our shear stress, is equal to mu, our viscosity, multiplied by gamma dot, our shear rate. So we can see this Newtonian fluid down here. We just have this nice linear relationship between shear rate and shear stress. And the slope of this line is mu, our viscosity. Plotted differently, we can look at our apparent viscosity, eta, against our shear rate, and we can see that our Newtonian fluid, as expected, has this nice constant function. A non-Newtonian fluid, on the other hand, is a fluid where tau, our shear stress, is equal to some unknown function of our shear rate. So we know that there is some relationship between the two terms, but we don't know what that function is. And in our plots down below, we can see how for our dilatant or shear thickening fluid, or our pseudoplastic, our shear thinning fluid, or our Bingham plastic, there is some clear relationship between tau and shear rate, but there's not a constant relationship. Similarly, we can see that this plot of our apparent viscosity versus shear rate, our dilatant or shear thickening fluid increases in viscosity as we see an increase in shear rate, and our pseudoplastic or shear thinning fluid sees a decrease in viscosity as we increase our shear rate. So kind of to succinctly define what a non-Newtonian fluid is, we can say that a Newtonian fluid is a fluid with a constant viscosity, while a non-Newtonian fluid is a fluid with a non-constant viscosity. As overwhelming as the topic of non-Newtonian fluids may seem, really it just boils down to non-Newtonian fluid is a fluid with a non-constant viscosity. So with that in mind, let's go ahead and take a look at a few different examples of non-Newtonian fluids. My favorite, or maybe the most classic example, is oobleck, the classic mixture of cornstarch and water. And oobleck is an example of a shear thickening fluid. So when you have your cornstarch and water mixture just sitting in a bowl, it looks like a liquid, it pours like a liquid, and it has the low viscosity of a liquid. However, as soon as you start to shear it or apply a force to it, it thickens such that you can ride a bike across it, or you can walk across it, or you can kind of pick it up and put it into a ball and play with it. So that's one example of a shear thickening fluid. Paint is another example of a non-Newtonian fluid. A paint is going to be thin as you're painting it, and then you want it to thicken while it's drying. So this is an example of a shear thinning fluid. as you're shearing it quickly, rolling it or brushing it across your wall or your canvas or whatever, it has a very low viscosity so that it spreads easily. However, as soon as you're done spreading it on your wall or on your canvas, you want it to thicken so that it doesn't drip and run. And so when you remove that shear rate, the viscosity increases. So paints another common example of a shear thinning fluid or of a non-Newtonian fluid. The third example we'll look at is toothpaste, and this is a great example of a Bingham plastic. When it's inside the tube, it's basically a solid. Yet as soon as you kind of start to apply force to it, you can squeeze it out and it behaves like a liquid. So that's a characteristic of a Bingham plastic, where at rest it has some yield stress that needs to be overcome before it can start to flow. However, as soon as you get it moving, it's going to flow and behave like a liquid, admittedly a high viscosity liquid. And then finally, kind of as a general category, we have slurries. And by definition, a slurry is a material or a fluid with particles suspended in it, and those particle interactions yielding some non-constant viscosity. And usually a slurry, you're going to have some sort of specialized viscosity model. So AFT software has an actual specialized SSL or settling slurry module that can help capture some of that non-constant viscosity behavior. However, we'll also talk about a couple of specialized viscosity models for modeling pulp and paper stock slurries. And so just a slurry in general has some non-constant viscosity. It's an example of, we don't really have a well-defined model, but we can say that at the very least, we know it does not have a constant viscosity, which would make it a Newtonian fluid. So these are kind of 4 different examples of fluids you may have encountered in your everyday life. Certainly there are thousands or millions more out there. These are just kind of 4 general categories. So with that overview of non-Newtonian fluids and what they are, we're going to go ahead and look at modeling non-Newtonian fluids, and specifically modeling them in AFT software. So AFT software offers 5 non-Newtonian fluid models, kind of 4 specific ones and 1 catch-all that we'll talk about a little bit later. And then, of course, there is our settling slurry module, add-on module that can be used to capture more detailed slurry behavior. So we're first going to talk about pulp and paper stock models. And in particular, we're going to talk about the Duffy method. I didn't really have any ordering here other than when you go into the system properties window and you open up your viscosity model, the very first viscosity model you'll see, other than a Newtonian fluid, is this paper stock Duffy model. So the Duffy method is just kind of a general model for use to model pulp stocks in pipes. Pulp being kind of wood shavings that you use eventually for paper. And to use the model, the user is going to select a pulp type here and a pulp consistency. And then once you've defined this model, Fathom or Impulse is going to go through and determine the head loss in each pipe using correlations based on velocity. And these correlations come from the Technical Association of the Pulp and Paper Stock Industry, or TAPI, and they're pretty broadly used a set of correlations. Similarly, we have as the second model that AFT offers the Brecht and Heller method. And this, of course, again, we're going to see on the viscosity model tab, and our viscosity model is just the next selection down. This model is a more conservative model, again, for pulp and paper stocks. And conservative here, I mean that all else held constant, the Brecht and Heller method will give larger pressure drops across each pipe than the Duffy method. So there will be some differences between the exact type and the consistency, but if you were able to use the same type, the same consistency, the Brecht and Heller method would give you a more conservative results than the Duffy method. Again, for this Brecht and Heller method, the user will select a pulp type and a pulp consistency. And now once, when they go to run the model, AFT software is going to determine the head loss across each pipe using correlations based on Reynolds number and a corrected friction factor. So that brings us to the next model that AFT software offers, the power law fluid. And now this is going to be a very common model used to capture many non-Newtonian fluids. In my experience, it's maybe one of the most broadly used or broadly followed model. And really all we say with it is that tau, our shear stress, is equal to K, a constant, multiplied by our shear rate raised to the n power, another constant. Put differently, we can say that eta, our apparent viscosity, is equal to that same constant K multiplied by our shear rate to the n-1 power. So both of these equations are power law functions, which is where this name comes from. We have our dependent variable equal to a constant multiplied by our independent variable raised to some power. And now in these models, the user is going to define K and N, where K is our flow consistency index with units of viscosity, and N is our flow behavior index, which is unitless. And N kind of characterizes whether this fluid is shear thickening or shear thinning. The power law model can capture both. When N is greater than 1, we have a shear thickening fluid. And when N is less than 1, we have a shear thinning fluid. And it's important to remember as you look at if the fluid is shear thickening or shear thinning, that you recall or that you keep in mind which form of this power law equation you have. If you're looking at this, eta is equal to K multiplied by the shear rate to the n-1 power, and this power term is just represented as one value, rather than greater than 1 being a shear thickening or less than 1 being a shear thinning fluid, you would see that a greater than 0 value is your shear thickening, while a less than 0 value is your shear thinning fluid. And I guess to come back to our flow consistency index value here, K is almost always shown as having units of viscosity, centipoise, or over here, the default, we could see pound mass per hour foot. However, strictly speaking, K would have units of viscosity multiplied by seconds to the 1 over n or 1 minus n power to make sure that eta, our apparent viscosity, actually has units of viscosity. So really we want the units of K to cancel out with the 1 over second units of our shear rate raised to the n-1 power. But for pretty much any practical purpose, we can treat K as having units of viscosity. And then when we go ahead, once we've defined these parameters, and we run our model, AFT software is going to adjust the friction factor for each pipe, or I guess determine the friction factor using a power law Reynolds number. So we're going to take that power law Reynolds number, which incorporates K and N, and use it to find friction factor. And then we can kind of just plug that friction factor into our standard Darcy-Weisbach loss model. If any of you guys are interested in seeing more about some of these equations, you can go ahead and look at them in the help file for Fathom or Impulse. I just got done kind of refreshing some of our discussion in there and our documentation, and we've got some good materials on there to show what those equations look like. So that brings us to our last kind of named model or specific model is the Bingham plastic fluid or Bingham plastic model. And this is another common model that's going to be used to capture a fluid with a yield stress. Again, that's that fluid where at rest it doesn't want to flow, and you apply a small amount of stress and it still doesn't flow until you exceed some yield stress, at which point it starts to flow again. So in this model, we can say that eta, our apparent viscosity, is equal to that yield stress divided by our shear rate plus our rigidity coefficient or our plastic viscosity. So the user is going to define SY, our yield stress, and RC, our rigidity coefficient in the software. And then we'll go ahead and take those parameters and again use a corrected Reynolds number to find that friction factor. And I'll point out here that depending on the source of your data or the source of the literature you're reading about the Bingham plastic model, this yield stress and the rigidity coefficient may be written out as a few different parameters. Sometimes yield stress is written out as tau y or tau 0, just indicating it's that yield stress. RC could be written as mu infinity, or denoted as the plastic viscosity. But really it's just that viscosity value to define the slope of our viscosity curve. So the last model we'll look at, or that AFT software offers, is the homogeneous scale-up model. And now this model is kind of our broadest possible one, and it's really used for any fluid type. Again, you'll find it under this viscosity model tab, and you'll click the drop down and go all the way down to the bottom to choose homogeneous scale-up. And here, the user is going to enter test data for pressure loss versus velocity. So this you would obtain by flowing your fluid through a pipe of a known diameter, and you'd measure your velocity value, and you'd measure your head loss value. And this model isn't so much a numerical equation that you can use to describe the fluid flowing in any pipe or any system. Rather, we're going to take that test data and we're going to scale it to the system model based on pipe diameter. So in this test data, we've said that we tested this in an 8-inch pipe, but of course our system won't only be an 8-inch pipe. So instead we can correlate it to a 10-inch pipe. So we can see these blue boxes are original data for that 8-inch pipe. And when we scale up our data to this 10-inch pipe, we will of course see a lower pressure drop for a given velocity value. And just for kind of comparison's sake, we can see this red line is our power law model, which matches pretty well against our test data, except for right here, which is our laminar to turbulent transition zone. So this homogeneous scale-up model isn't necessarily any better or any worse than some of these more mathematical equations we've described previously. However, if you don't know what kind of non-Newtonian fluid you have, all you know is some test data about it, this homogeneous scale-up method is a pretty great tool to kind of capture any of that unknown behavior. So now that we've talked through these few different examples, few different models that AFT software offers, we're going to go ahead and talk about some examples and look at these models in action in AFT software. So our first example we're going to look at is for a power law fluid, and specifically we're going to look at our non-Newtonian phosphates pumping example. This is a default example installed with Fathom that you can use, for whatever you want. I think we walk through it potentially in our quick start guide. No, that's not correct. We don't walk through it in the quick start guide. It's just an example model that has instructions along with it. But yeah, so this example is cool. We're going to see how viscosity is a function of velocity for this power law fluid, or really any non-Newtonian fluid. So let's go ahead and check it out. I pull this up here quick. This is our non-Newtonian phosphates pumping example. This is the metric version just because we'll look at one metric and one US, I believe. But we're going to move to this power law scenario, and we can see that we have 3 different pumps set to different flow rates: 1,080, 720, and 1,440 cubic meters per hour. We've got the same upstream and downstream definitions. And each of these pumps aren't defined as being on a pump curve, but rather with that sizing option. So the Fathom is going to force 1,080 cubic meters per hour through this pump, regardless of the head rise at the pump needed. So if we run this model, which I've done already, we can go ahead and look at the output here. And I guess to go back to the workspace real quick, pipes 1 and 2 are the same diameter, so they'll have the same velocity and the same viscosity. Pipe 11 and 12, again, will have the same velocity and viscosity, and pipes 21 and 22 will have the same velocity and thus viscosity. So when we go to the output, we can see that here. Pipes 1 and 2 have a volumetric flow rate of that 1080, a 4.1 meter per second velocity, 564.8 centipoise viscosity, and all the other results that are relevant to the system. When we look at pipes 11 and 12, we have a lower flow rate, we have a lower velocity, and we have a higher viscosity. So that tells us that we have a shear thinning fluid. And we can confirm that by looking at pipe 21 and 22 that have a higher flow rate than our base, and thus they have a lower viscosity, which again indicates that we have a shear thinning fluid. And if we go up to our system properties here on the toolbar or under the analysis menu, we can see this fluid has just been defined as a little bit denser than water, with a dynamic viscosity of just 1 centipoise. So again, that's the viscosity of water. And when we go into our viscosity model tab, we've defined this as a power law fluid. And specifically, we've given this a K value of 28.28, that's kilogram per second meter. Let's go ahead and take a look at this value in centipoise. We've got 28,000 centipoise. That's pretty high, but of course, we're never going to be at that stationary fluid. And then our N value is 0.1364. And that, if you recall from earlier, is it means that we have a shear thinning fluid. It's less than 1, which is that shear thinning. And that's very consistent with the viscosity results we've been seeing over here, which is cool to see. You'll notice that this example has been defined with the calculate from rheological data option. So the example walks you through how to enter some rheological data, and then we'll go ahead and calculate these constants for you. We won't talk about that too much right now. We'll look at it a little bit later in the presentation, but it's a cool tool if all you have is the raw data and you don't actually know the constants themselves. So having seen this viscosity, how this changes, we're going to go ahead and go back and kind of take a look and check some of Fathom's results. So we saw how that viscosity changed with our velocity, and we can actually go ahead and plot those values and see how they compare or how they fit our power law equation, saying that eta, our apparent viscosity, is equal to K multiplied by our shear rate raised to the n-1 power. So when we take our velocities and determine a shear rate value, and then plot apparent viscosity against it, we get these nice 3 data points. And we can use Excel's built-in curve fit tool to compare or to determine what our constants are. And we can say that eta is equal to 23,924 multiplied by gamma, our shear rate raised to the negative 0.866 power. So again, remember that this value here is n-1. So if we want to actually get n, we have to add 1 to this, and we get n is equal to 0.1341. And if we compare this against the inputs we put into Fathom, we can see that our n values match up exactly, which is cool. But our k values are just a little bit different, 28,600 versus 23,900. And that's expected. It's hard to calculate an exact value for shear rate. And we'll also talk a little bit more about how the shear rate I've calculated here is our bulk shear rate. We just used it from the bulk velocity as opposed to our wall shear rate, which is measured at the actual wall of our pipes. And again, we'll talk about this a little bit later, but that difference right there, along with the fact that we only have these 3 data points, means that this difference between our Fathom input and this kind of back calculated result is an acceptable difference. But it's cool to see that we can curve fit against our Fathom results and get good consistency with our inputs. So the next example we'll look at is a Bingham plastic fluid. And as you recall, a Bingham plastic has a yield point. The system must provide pressure, some minimum pressure value to meet that yield point. And until you reach that, the system won't see any flow, which can yield some kind of interesting behaviors. So with that in mind, let's go ahead and check out another example, our pump sizing and selection example. Now this example model is by default is installed with AFT software. Now I have gone ahead and made a few modifications from the example because the example uses some control valves that I don't want to actually control the flow. So I've gone ahead and set them to be fully open with no control. So in this control valve, we don't have any losses, it's just none. So the flow is kind of moving along this pipe run as if this control valve didn't exist. And on our right leg, we have this other control valve, which again is set to be fully open, no control. But this time we have a CV value of 200. So there is some loss like you would see across any valve along this right pipe leg. Another change I made was I removed the heat exchangers, which were here because they were adding a lot of losses to the system that kind of exacerbated the losses associated with the Bingham plastic. But in the base example, when we run this model, we see flow distributed along both flow paths, and that's what we want to see. However, when we send flow in this example, when it's a Bingham plastic, I guess I'll show those inputs too. We've got just kind of water with a little bit higher viscosity. I guess this is pound mass per hour foot, we'll say centipoise. So we've got water with a nice normal viscosity, but we're going to alter that with the Bingham plastic. And we're going to say that our actual viscosity is 5, and we have a yield stress associated here. So now when we flow fluid through the system, we get about 500 or 450 gallons per minute, moving at not very fast velocity. We can see that this is a pretty turbulent flow. But we see a pretty good amount of pressure drop along our pipe because this fluid, this Bingham plastic, is pretty viscous. However, as soon as we split between our two flow junctions, we actually see that flow, all of our flow moves along this left leg that has no losses at the control valve, while no flow moves along this left leg. And that's pretty different than what we might expect for a Newtonian fluid. However, for this Bingham plastic, where there is that yield stress, this is somewhat expected behavior. This is telling us that when the fluid is moving along a single flow path, we can meet and exceed that yield stress. However, when we have these two parallel flow paths, we no longer can meet that yield stress. And if we actually had flow moving through both of these, well, we wouldn't have flow. It would be stagnant because we can't overcome that pressure differential. So Fathom actually will solve the math and force all of our flow through this pipe leg with lower losses, because when it's moving through that one pipe leg, we can see we actually get flow. And then on this other pipe leg, we can't overcome the yield stress, and so we see a stagnant region. And I think that's kind of cool to see how that Bingham plastic works out in your system with multiple flow paths. And it's a good reminder that in a real system, which has more complications than even this example, you have parallel, you have in series flow paths, and a very networked system, there's a potential that some of your legs might not actually see flow, just because the system can't meet that yield stress demand. So that's kind of a cool example of the Bingham plastic fluid, and a good reminder of A, why it's important to carefully consider your system, and B, why a tool like Fathom can be really powerful to help you diagnose some of those yield stress concerns. So if we go back to our slides, as a brief recap, we can say that left system branch had no losses at our control valve and saw some flow, while the right system branch had some losses at our control valve and saw no flow because it couldn't overcome that yield stress. And that has some interesting implications for a pump system curve. Specifically, that Fathom might not be able to generate a system curve at low flows. So if you think about that system, how parts of it saw no flow, if part of your system has no flow, like this example, a system curve might not be valid for those low flow rates. Now, as a refresher for those of you who might be unfamiliar with pump system curves in Fathom, a pump system curve is going to look, for example, like this. Here's our pump curve, here's our system curve, and we can see that as our volumetric flow rate lowers, the head loss in our system decreases. Now, Fathom has no way of knowing this system curve like it knows this pump curve. So instead, Fathom will go through and calculate system losses at different flow rates, just kind of by forcing 25, 50, 100 gallons per minute through your pump. However, if your system is set up such that your pump doesn't have enough pressure to force these low flow rates, or at these low flow rates you can't meet that yield stress, some of these lower portions might not be valid possibilities in your system. And as a result, when Fathom tries to calculate these values, it's going to run into an error. Now, I tried to make an example showing this, and it's a little more complicated than you might think. It takes a very specific set of system requirements. And I have a few examples from customer models I've helped during my time as a technical support engineer. But of course, I can't show them because they're proprietary and we respect our customers' privacy. But if I could show them, we would see that when Fathom tries to generate these points, it actually runs into an error. And you have to restrict the flow to above this minimum value to only generate this portion of the system curve. So it won't happen in every system, but if you're ever using a Bingham plastic and you try and make your pump system curve and you run into an error, just kind of think about, well, okay, well, maybe my system just isn't valid at those low flow rates, and you can restrict that system curve accordingly. So the last example we'll look at is a transient system. And this is my favorite. In Impulse, we can actually model non-Newtonian fluids too. So we can use the same correlations as Fathom, just updated with each time step. So it's kind of a pseudo-steady approximation. There's not really a great way to actually apply these viscosity models in a truly transient manner. So we'll just use this pseudo-steady approach. So let's go ahead and take a look at Impulse. So this model I've modified a pretty good amount, but you might recognize this portion of it from our valve closure example installed by default with Impulse. And what I've done is I've gone through and replicated the system 5 different times so we can look at 5 different viscosities. And specifically, this 200 system is our Newtonian fluid. We've got water basically. Actually, we do have water in the system. So this fluid is Newtonian. Pipes, this 0, 100, and 100 system are our shear thickening fluid with a power law model. And this is a shear thinning fluid. N is 0.8 in this 100 system, N is 0.6 in the 0, 100 system. And then in our 300 and 400 series, we've got a shear thickening fluid. N is equal to 1.2 in our 300 series, and N is equal to 1.4 in our 400 series. So when we run this system, in steady state, we can see that, I thought I had viscosity in here somewhere. We can see that we have different flow rates in our system. We can see a decreasing flow rate as that viscosity increases with our shear, with our velocity. Let me go ahead and add our fluid viscosity in here into my results. And we can see here that this is, we want this in centipoise. This 200 system is water. And as we lower that end value, we see a lower viscosity. As we increase that end value, we see a higher viscosity. Now, when it comes to a transient results, and I'm going to go ahead back to my slides here real quick, we have to ask the question, what do we expect to see in our transient power law fluid? Well, if we think about kind of the cross-sectional velocity profile of our system, in turbulent flow, we have kind of that inner region, a fully developed turbulent flow, which has a pretty constant velocity. But as we change the velocity of our fluid, we change that boundary layer. So if I kind of draw this here, when we have our pipe, we have some velocity profile that might look like this, where we've got a low velocity and high wall friction over here, and we've got this kind of constant higher velocity that's not seeing our wall effects, and then again, we've got the boundary layer on the other side. And we can say that the fluid boundary layer, this area here, narrows and expands for our shear thickening and shear thinning fluids, respectively. And we can say that when we have a shear thinning fluid and that lower frictional resistance, our pressure wave amplitude is going to increase because we have less friction slowing the fluid down. Conversely, when we have our shear thickening fluid, we'll have a higher frictional resistance, and thus our pressure wave amplitude decreases. I'm going to go ahead and clear out my drawing here because we're going to go back over into Impulse and actually look at that exact behavior. So in each of these systems, we have a valve closing in about a second. And if we look at our graph results for the just upstream of that valve, we can see this flow rate kind of being closed off over the course of 1 second. And so we can initially see that there's some variation in the flows in each system, but once we close off the valve, we can see a fairly uniform response. However, if we zoom in on this pressure peak here, we can actually see that as our N value increases, the amplitude of our pressure wave decreases. So our most shear thinning fluid has the highest pressure wave amplitude, and the least shear thinning fluid, or I guess the most shear thickening fluid, has that lowest pressure wave amplitude. Now, some of these differences are related to the difference in the steady state operation, but a good part of them are related to just the behavior in that transient system. And now, of course, this isn't a very large spread. We're looking at the difference of, I think this would be 1 Pascal between each of these major grid lines. But it is a difference, and it's interesting to see. As I've been looking at this, I've found some cool research into this transient behavior, and this behavior that Impulse is predicting is very consistent with literature sources. And so to me, it's cool to see how you can define these basic inputs, these kind of fundamental viscosity inputs, and Impulse will take those into consideration as it looks at the other conservation equations and spit out these results consistent with the real fluid behavior. So I think this is cool to see how the non-Newtonian behavior of a fluid impacts some of these transient results in potentially unexpected ways. So if we go back to our slides here, just to recap, we can see this difference in our pressure wave depending on our non-Newtonian fluid. So those are all the examples that we'll talk about here. And now we're going to look finally at rheological data. And this is an important topic because it's important when you're modeling your non-Newtonian fluid that you define your model correctly. So we'll start by asking, what is rheology? Well, rheology can be considered the study of the flow of matter. So liquids, gases, and soft solids all flow. And the term rheology comes from the Greek phrase panta rhe. I hope I'm pronouncing that correctly, meaning everything flows. So rhe meaning flow, ology, the study of, rheology is the study of flow. Rheometry is a similar root. We got rheo up front, and we can say that it is the experimental characterization of a material's rheological behavior. So, when you're studying a fluid's viscosity or how it flows, you're doing rheology. When you capture that data, you are performing rheometry. And there's a few different ways you can determine that rheology. One common, I guess the common definition or the common equipment you would use is a rheometer, which is just an experiment or an experimental device used to characterize the rheology of a non-Newtonian fluid. I suppose you could use it on a Newtonian fluid too, but it wouldn't be all that interesting because, well, you'd measure it at different velocities or different shear rates and get the same viscosity back out. So to look at some experimental equipment, we have a few different common types that I'll talk about. A parallel disc, where you have two rotating discs with your fluid in between, inducing a shear rate and measuring the torque or the stress needed to force that. A cone and plate is another one. You put a spinning cone on top of the plate with fluid in between. Again, you're going to rotate it and induce a shear rate and then measure the torque needed to do so. And another common one is a couette or cup and bob rheometer, where you put a bob inside of a cup containing your fluid, you spin the bob and determine your viscosity or your shear stress. And there's a few different variations of what that looks like. Another class of rheometers is what I'm going to call empirical measurement. So these kind of devices is what you would see in a laboratory setting. However, sometimes you don't want to go into the lab, you just want to capture that field or empirical data. And so here you'd go through and capture your pressure drop versus velocity data, kind of like what we looked at for the homogeneous scale-up model. And across all of these, fundamentally, we're trying to characterize the shear stress at a given shear rate. We want to make one of these plots so that we can describe the behavior across an entire range of flow rates. And as we try and capture that behavior, we have a few different types of data we might achieve. A common type is shear stress versus shear rate data. However, it's important to remember that not all shear rates are equal. So there's kind of two different forms. One is the wall shear rate, and this is the shear rate measured at the wall of your rheometer. And because we know that the velocity profile changes in the test, in the fluid, and because we know that our viscosity models, our tau, our shear stress, is very highly dependent on that velocity profile, we have to be careful where we're measuring it. So this wall shear rate we're going to measure at the rheometer wall, whereas our bulk shear rate is going to be determined using the average pipe velocity. So our experimental rheometers are likely going to report this wall shear rate, while our empirical data, we have no way to actually characterize that velocity profile inside the pipe. All we know is the bulk fluid flow. So that's going to give us our bulk shear rate. And these two shear rates are equal only for Newtonian fluids. Of course, since we're measuring or we're dealing with a non-Newtonian fluid, we have to make sure we distinguish and can convert between them. So AFT software is going to ask for this bulk shear rate data. It was built on the assumption that for the most part, an engineer is going to have this kind of empirical style data. However, it's still very common for engineers to have the experimental data. So one improvement we're looking to make for Fathom 12 and Impulse 9 would be to add in multiple options for this rheological data input. However, the help file for Fathom 11 right now and Impulse 8 cover this idea that not all shear rates are equal and how to convert between these two types with more detail. I'm not going to get into it right now because it does involve some math, but if you're ever interested, go ahead and check out the latest releases of Fathom 11 and Impulse 8 so you can look at that for yourself. And I stress the latest releases because I did just get done refreshing some of that content. So the old content covers it a little bit. However, if you're able to upgrade to the current releases of Fathom 11 and Impulse 8, you'll be able to get an even better and more thorough description of what that process looks like. Some other forms that your data might take are viscosity versus RPM. Those experimental setups I showed are rotating objects. So the base data collected is going to be RPM, and maybe they're reporting viscosity. So again, this is common data from that rotational rheometer. And we can convert our RPM to our shear rate and then find viscosity model constants from that. However, the conversion between RPM and shear rate really depends on our test geometry. So if all you know is the final data and you don't know anything about the setup itself, it's going to be a little tricky to actually capture or to model this fluid. However, once you have some of the test geometry, we can know that shear rate is equal to the velocity divided by the distance between our surfaces. And so as soon as we know that geometry, we can easily determine our actual shear rate value. Another type of data you might have is our viscosity versus shear rate data. And again, this is going to be common data from that rotational rheometer. We can convert this RPM to shear rate or have the shear rate on its own. And from here, we can directly find our viscosity model constants. Another common type is viscosity versus velocity. Maybe you know flow based on empirical measurements at a velocity, and you can measure that viscosity. And so here you'd want to convert your velocity to bulk shear rate. I believe it uses the equation 8 multiplied by the velocity over the diameter of your pipe will give you that bulk shear rate. And then from there, you can determine that wall shear rate, which again, our help file for Fathom 11 and Impulse 8 goes into with a lot more detail. And once we have that wall shear rate, we can use our viscosity and that wall shear rate to find our viscosity model constants. So again, these are just kind of three potentially common types of rheological data. Goodness knows there's an endless number of forms you might have data in. If you ever have data you don't know what to do with, feel free to send it over to us at support@aft.com. Myself or one of our other technical support engineers will help you out, kind of learn what it means to use it. And we'd love to see some of that raw data as examples of what engineers are commonly working with. I'll take a shameless plug at our Platinum Pipe Award contest, where we ask users to submit example models and example situations where we've used our software. So if you're ever modeling a system with that non-Newtonian fluid in it, we would love to have you submit your model, submit your system for consideration for our award. Winners receive a pretty substantial cash prize and software credit for their company. And we would love to be able to have an example of a real system with these types of fluids, so we can show off those capabilities to other users and really highlight the benefit of using some of these viscosity models. I believe entries are usually around October, so you've got some time still. And we always send out a few reminders with our newsletters, so if you're subscribed to those, you'll see those reminders. So that's kind of all I have today. We're going to go through a quick recap. A non-Newtonian fluid is a fluid with some non-constant viscosity. As simple as that. Non-Newtonian fluids are an admittedly complex subject. Hopefully today's webinar has given you that fundamental basis you need to know to realize that non-Newtonian fluids are an approachable and attainable subject to be knowledgeable about. However, there is, of course, an infinitely complex series of kind of fluids you can look at, and you could spend your entire academic career learning about non-Newtonian fluids and becoming more knowledgeable. So it's pretty, it's for pretty much every engineer. It's attainable and easy to learn about non-Newtonian fluids to the point of using them and using AFT software to make that more simple. But of course, you can always keep diving in and learning more about the topic. Numerous models exist to describe their behavior. We've talked about 5 of them, I believe, but certainly we haven't captured all of them. One common model we didn't talk about today was the Herschel-Bulkley fluid, which kind of combines that power law model with the Bingham plastic and its yield stress. And that Herschel-Bulkley model is something we're looking to add into Fathom 12 and Impulse 8. So when those come out, hopefully later this year, make sure to upgrade so you can check them out, because it's a cool fluid model to be able to capture both of those. And finally, AFT, I guess not finally, I have one more bullet point, but AFT software incorporates those models for the engineer, making it super easy to model your system that might be pretty complex to model by hand or to calculate by hand. And finally, those updated Fathom and Impulse help files have really good information on non-Newtonian fluids, going a little bit more in detail into the math behind them, and into some of those rheological data considerations. Of course, every version will have some commentary on this topic. However, I encourage you to upgrade to releases here in 2021 for Fathom and Impulse so that you can really get your hands on my updated materials in there, because they do a really great job of explaining some of these more complex subjects. So that's all I have today. Looks like it's 10:58, so I'm gonna let you guys go on with the rest of your day, right on time. I'm sure many of you submitted questions. Hopefully Ben was able to answer some of them. Otherwise, I'll be taking a look at them later this week, and hopefully we'll get back to you. Of course, if you have any other questions, you can reach us at support@aft.com, and our team of experienced engineers will get back to you as soon as we can. Thanks for joining in, everybody. That's all I have for you today. Have a good rest of your day, or if you're watching this in the future, I hope your future day is good as well. Thanks, everybody, for joining.